This episode is brought to you by Cisco Educational Premium. Did you know the Fokker-Planck equation is a partial differential equation? In statistical mechanics, the Fokker-Planck equation is a partial differential equation that describes the time evolution of the probability density function of the path of the velocity of a particle under the influence of drag forces and random forces as in Brownian motion. The equation can be generalized to other observables as well. It is named after Adrian Fokker and Max Planck, who described it in 1914 and 1917. It's also known as the Kolmogorov-Ford equation after Andrei Kolmogorov, who independently discovered it in 1931. When applied to particle position distribution, it is better known as the Smoluchowski equation after Marian Smoluchowski, and in this context, it is equivalent to the convolution diffusion equation. The case with zero diffusion is the continuity equation. The Fokker-Planck equation is obtained from the master equation through Cramer's Moyal expansion. The first consistent microscopic derivation of the Fokker-Planck equation in the single scheme of classical and quantum mechanics was performed by Nikolai Bogolubov and Nikolai Krylov in one special dimension X for an Ito process driven by standard Wiener process Wt and described by the stochastic differential equation SDE. dxt is equivalent to mu xtt dt plus sigma xtt dwt with drift mu xt dt with drift mu xt t and diffusion coefficient d xtt equivalent to sigma square xtt on 2. The Fokker-Planck equation for the probability density pxt of the random variable xt is partial on partial t pxt is equivalent to negative partial on partial x mu xt pxt plus partial square on partial x square dxt pxt. While the Fokker-Planck equation is used with problems where the initial distribution is known, if the problem is to know the distribution at previous time, the Feynman-Cass formula can be used, which is a consequence of the Kolmogorov-Backward equation. The stochastic process defined as we have looked at in the Ito sense can be written within the Stratonovic convention as a Stratonovic SDE. dxt is equivalent to u xtt minus half partial on partial xt dxtt dt. It includes another noise-induced drift term due to the diffusion gradient effects if the noise is state dependent. This convention is more often used in physical applications. Indeed, it is well known that any solution to the Stratonovic SDE is a solution to the Ito SDE. The zero drift equation with constant diffusion can be considered as a model of classical Brownian motion. Partial on partial t pxt is equivalent to d naught d0 partial square on partial x square pxt. This model has discrete spectrum of solution if the condition of fixed boundaries is added 0 less or equal to x, s less or equal to l. It has been shown that in this case an analytical spectrum of solutions allows deriving a local uncertainty relation for the coordinate velocity phase volume delta x delta v greater or equal to d naught, where d naught is a minimal value of a corresponding diffusion spectrum dj, while delta x and delta v represent the uncertainty of coordinate velocity definition. A standard Wiener process is generated by the stochastic differential equation dxt is equivalent to dwt. Here the drift term is 0 and the diffusion coefficient is half. Thus, the corresponding Fokker-Planck equation is partial pxt on partial t is equivalent to half partial square pxt on partial x square. This is the simplest form of a division equation. If the initial condition is px0 is equivalent to sigma x, the solution is pxt is equivalent to 1 on root 2 pi t e raised to negative x square on 2t. The Ornstein-Uhlenbeck process is a process defined as dxt is equivalent to negative a xt dt plus sigma d wt with a greater than 0. Physically, this equation can be motivated as follows. A particle of mass m with velocity vt moving in a medium, like a fluid, will experience a friction force which resists motion, whose magnitude can be approximated as being proportional to a particle velocity, that if a vt with a being constant. Other particles in the medium will randomly kick the particle as they collide with it, and this effect can be approximated by a white noise term, sigma dwt on dt. The Newton's second law is written as m dvt on dt is equivalent to negative a vt plus sigma dwt on dt. Taking m to be equivalent to 1 for simplicity and changing the notation as vt approaches xt leads to the familiar form dxt is equivalent to negative a xt dt plus sigma dwt. The corresponding Fokker-Planck equation is partial pxt on partial t is equivalent to a partial on partial x xp xt plus partial plus sigma square on 2 partial square pxt on partial x square. The stationary solution partial tp is equivalent to 0 is pssx is equivalent to root a on pi sigma square e raised to negative x square on sigma square. In plasma physics, the distribution function for a particle species SPS xvt takes the place of the probability density function. The corresponding Boltzmann equation is given by partial ps on partial t plus v dot del ps plus zse on ms e plus v cross b dot del v ps is equivalent to negative partial on partial vi ps del vi plus half partial square on partial vi partial vj ps del vi ps delta vi delta vj, where the third term includes the particle acceleration due to the Lorentz force, and the Fokker-Planck term at the right hand side represent the effects of particle collisions. The quantities delta vi and delta vi delta vj are the average change in velocity a particle of type s experiences due to collision with other particle species in unit time. Expression for these quantities are given elsewhere. If collisions are ignored, the Boltzmann equation reduces to the Vlasov equation. The Smolojewski division equation is the Fokker-Planck equation restricted to the Brownian particles affected by an external force Fr. The importance of this equation is it allows for both the inclusion of the effect of temperature on the system of particles and a spatially dependent diffusion constant. Brownian motion follows that the Langevin equation, which can be solved for many different stochastic forcings, with results being averaged, canonical ensemble in molecular dynamics. However, instead of this computationally intensive approach, one can use the Fokker-Planck equation and consider the probability pvt dv of the particle having a velocity in the interval v plus dv when it starts its motion with feed, not a term zero. Paying a partial differential equation, the Fokker-Planck equation can be solved analytically only in special cases. A formal analogy of the Fokker-Planck equation with the Schrödinger equation allows the use of advanced operator techniques known from quantum mechanics for its solution in a number of cases. Furthermore, in the case of overdamped dynamics, when the Fokker-Planck equation contains second partial derivative with respect to all spatial variables, the equation can be written in the form of a master equation that can easily be solved numerically. In many applications, one is only interested in the steady state probability distribution P naught x, which can be found from partial pxt on partial t is equivalent to 0. The computation of mean fast passage times and splitting probabilities can be reduced to the solution of an ordinary differential equation, which is intimately related to the Fokker-Planck equation. In mathematical finance, for volatility smile modeling of options for locality volatility, one has the problem of deriving a diffusion coefficient sigma xt t consistent with a probability density obtained from market option quotes. The problem is therefore an inversion of the Fokker-Planck equation. Given the density fxt of the option underlying x reduced from the option market, one aims at finding the local volatility sigma xtt consistent with f. This is an inverse problem that has been solved in general by Tupaia 1994-1997 with a non-parametric solution. Brigo and Mercurio 2002-2003 propose a solution in parametric form via the particular local volatility sigma xdt consistent with a solution of Fokker-Planck equation given by a mixture model. Every Fokker-Planck equation is equivalent to a path integral. The path integral formulation is an excellent starting point for the application of field theory methods. T is used, for instance, in critical dynamics. Derivation of the path integral is possible in a similar way as in quantum mechanics. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So, do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.